Sorry for this.
Yeah, it's in progress now, right? And there's any other question? I think there's someone saying something in the chat. No? Okay. Great. So although we cannot like say that a phylogenetic tree or a group of species speciate under a large S or a smaller S, a sympatric or a parapatric mode of speciation, we know that our signatures can be detected and somehow they are related with what we observe. Of course, other processes can lead to the same patterns, can lead to the same phylogenetic tree properties, but we see here that the geographic mode of speciation leaves some important signatures. And because we work with this decreasing the mating radius or the home range, doesn't matter how we call, but because we have this structure in the space or a structure, a spatial structure of how individuals use this space, we want to understand better how non-continuous spatial configuration could leave signatures in these phylogenetic trees as well. And as I told you, we were going from a large S to a smaller S, from a more sympatric mode of speciation to a more parapatric mode of speciation. But we still have the allopatric mode of speciation, where we really have barriers, where we really have like things or islands where these individuals occupy in this space. And we decided doing the simulations under these scenarios where we have barriers between these individuals and what we can call more allopatric mode of speciation. And just going back here, I was expecting that because I was moving from individuals can reproduce with any other in the space to a more structured configuration where individuals could use only a smaller part of the space or their neighborhood. Because I was structuring this space and I observed that the effect on the phylogenetic trees was related with the acceleration of this phylogenetic tree, I was expecting that when I imposed a more allopatric mode of speciation, I would observe some signature left on the acceleration mode of speciation. And however, for my surprise, and maybe it was a kind of obvious, this didn't happen. So individuals were, there is a variation, of course. The accelerated mode decreased, the variation of the acceleration decreased in these models. But something that I was not expecting is that the signatures were going to be left on the balancing of these phylogenetic trees. And it's important here to say that the balancing of the phylogenetic trees is related with the, just let me move this bar here, is related to the number of species. So something that we observe is that when there is only one islet or only one thing, the number, as the number of species increases, the balancing of this, the unbalancing of these phylogenetic trees increases as well. But as we incorporate more structure in this space, as we incorporate more islands, we have smaller values of the unbalancing of these phylogenetic trees, making this less, decreasing the angle of the relationship between the number of species and the balancing of the phylogenetic trees. And this was surprising. So with a given number of species, for instance, 15 species, I would expect if there's only one space, there's only one island, that the balancing of the phylogenetic tree would be very high. But then under 4 things or under 4 islands, we observed that this would be smaller than 10, would be around 2 or 3. And we wanted to relate as well with data that we observed in the literature. And we were very surprised by that the balancing of these phylogenetic trees, at least these ones that are here on the left, we can, studying only the balancing of these phylogenetic trees and the number of species that we have in these phylogenetic trees, we can say almost precisely how many islands they evolved under. So these are the silver alliance plants. These are the tetragnatha spiders, and these are the sticta lichens. And we could relate very well the number of islands that they evolved under with their balance of the balance of their phylogenetic tree. However, sometimes we failed, and basically we failed for only one case, that was for the Darwin finches. These Darwin finches, they evolved for under many islands, very well studied, and but we cannot detect this with their number of species and their balancing. So if we put in this plot here, we say, oh, they evolved under one island. And something that can explain this, or we understand that can be one of the explanations for this case, is that these birds, they fly, and they can fly from island to island. And there is a very high gene flow between the different islands. And maybe these birds are, they see the different islands as on one space. And because of this, we also wanted to understand how migration could affect the speciation process. So how migration can explain some things. And we didn't evaluate in this work the signatures left in the phylogenetic tree, but we try to understand what are the processes that are making species form when we have a two-island system. And this was based in a very theoretical work as well, proposed by Manzo and Pellit, that based their work in the Hida-Hicks model, where we have two different islands, two sets of islands, and same number of individuals and everything, and individuals can migrate from one island to the other island. And so we start with the individuals migrating from different islands with a given probability. They reproduce with the compatible individuals inside the island, and then we identify species. And then we go again for another step of migration, reproduction, and then we identify species. So we wanted to understand how these species were the same in the different islands. If we look at different islands, there were like, if there were species that were in one island that were also in the other island, and if we had like endemic species. And we know there are many parameters in this model, and we kindly understand, I think we understand them very well. We know that the number of individuals in each island matters for the number of species that are formed. And also the genome size matters for the number of species that are formed. And something that we saw is that, the average number of species increases as we increase the genome size. And there is a maximum value here that we wanted to understand better how they were, how it was possible, what are the process forming these species here. That is related with the migration rate, or the migration probability, and the population size. So something we did was to understand the beta diversity index. The beta diversity index just gives you the information about the number, if the total number of species inside the islands, if the species inside each island are the same species that are in the total population, if we consider the whole set. So if beta is close to 1, it means that the species that we have in one island are different of the species that we have in the other island. And if beta is close to 0, it means that the species we have in one island are the same species we have in the other island. So beta close to 1 means that we have a more endemic case of species. And beta is close to 0, we have these species are everywhere. They are exactly the same. And we observed that there were, let me show here. So the yellow part here is a great value of beta, and it's close to 1, meaning that we have many endemic species here. And what was happening here was the process that we found that was happening here was the speciation by founding population. So one population from one island, individuals from one island migrates to the other island, and then they establish a new population there. It's almost a founding effect. But then we observed that there are also species, like the richness of species per island was also high under a greater value of migration probability. And we wanted to understand better what was happening. So we were making individuals go from one island to the other very many times, or with a high probability. So we were increasing the genetic flow between these two islands, and we were not expecting under this situation that we would even form species, but the species were being formed. And what we found that was the process that was making this speciation possible was the ring-like species that were forming. And I will explain better what is the ring-like species mode, but what we see here is that there are many, under a high migration probability, we have many ring-like species. And this is what we call the sympatric speciation induced by migration. And what I mean by this is that we have like one island here, individuals migrate to this island here, and then bring novelty, they bring genetic novelty to this island. And because of this species that was here originally is exactly the same species that is here. Because of the novelty that was brought from the other island, it breaks in a different species. Inside this island here, we have two species. Individuals of this group cannot reproduce with individuals of this group. But because they're linked somehow with individuals of the other island, we have only one species when we count the total configuration of islands. So this is what we call the speciation, the ring-like species, and it was sympatric speciation. It was a speciation that happened in one island that was induced by the novelty brought by the migrants. Okay, so we understood very well like what was happening in this space, and something that we didn't explore before and we wanted to understand better was the hybridization and extinction. We were only studying the number of species, how it leaves signatures in the phylogenetic trees, but we know very well from many data that the evolution is not that perfect binary phylogenetic tree. It's actually a reticulate evolution. A species form, species disappear, a species mix again. And we have, for instance, the hybridization, and by hybridization, I mean, we had like different species that in another time step, they establish again somehow the genetic flow between them, and they're again on one species. And we also have extinction, that only means that individuals of a given species, they all disappear, all of them cannot reproduce, and then in the next time step, we don't have these species anymore. So we wanted to understand this better because this matters a lot. There are many signatures that are left by extinction and by hybridization that we wanted to study. And just to explain better in terms of our graphic representation, what I mean by extinction is that the population decreases, and then disappears. If we do a branch in that phylogenetic tree, we'll finish at some point, we'll end up at some point, and we'll be cut there. By fusion or reversal, these are two kinds of hybridization that we have in our definitions here. We have a species that splits in different species, and then in the future they join again, and they are only one species again. And this can be represented in a phylogenetic tree by a bifurcation that joins again and form on one species. And by reversal is just because you need two speciation process to join again the individuals that pass to the species that pass through to speciation process related to their common ancestor. And this was a first work on this extinction and hybridization. We wanted to understand it better. And we found that extinction is something that doesn't matter the genome size we are working with. We see that extinctions, they are happening during the whole speciation process, and they have the same rate. But hybridizations, they happen mostly on the beginning of the speciation process, and then they remain constant or almost constant during the rest of the evolutionary time. And studying this large genome size was important because we realized it only with this work that this is something that we cannot detect with the original Derrida-Hicks model that works with infinite genomes. So for the Derrida-Hicks, hybridizations are likely not possible, while extinctions is still possible. And I don't know if you realize that so far I didn't talk about selection, I didn't talk about fitness. I just talked about a very neutral mode of evolution, right? Individuals are the same, they just need to find someone that is compatible, genetically compatible with them to reproduce, and doesn't matter the age rate. And then we decided that we wanted to understand better the selection and here should not be hybridization extinction, sorry. So we wanted to include selection, and to include selection, we used game theoretical approach. We wanted to understand how is cooperation evolution under a scenario where individuals are divided in species. And to do this, the only difference is that we made one of the zeros and ones C and D for work with a game theoretical approach. And we worked with a prisoner's dilemma game. So in the prisoner's dilemma, I think I'm explaining to people that know this better than I do. What is expected is that defectors will be the evolutionary stable strategy. And even if we start with a very low number of defectors, they will overcome all the cooperators because they have their payoff against cooperators is greater than the cooperators with cooperators. And because defectors playing against defectors have a higher payoff than cooperators against defectors. And we also knew about the evolutionary model that Novak proposed in, I don't know how many years ago. There was a very similar model that we have. It was in a lattice. Individuals could reproduce with their neighbors, and then you can define the neighborhood size here, and then you can compute their fitness based on how they interact with the individuals that are in their neighborhood. So we did this. We used the game theoretical approach with the prisoner's dilemma, and we wanted to understand how speciation affects both cooperation evolution and how cooperation evolution affects the speciation process. To do this, we worked with a very similar matrix that Novak worked. It's a simple prisoner's dilemma game. And something that we observed that was really cool, we still have the same, or basically the same results. There are some changes here on the cooperation frequency, on the number of cooperators that we form. And it depends on the value of B that we have in our payoff matrix. And the species richness, or the number of species that was formed, didn't have a big difference depending on the value of B. But something that was really curious that we observed was that the phylogenetic trees without game and with game, when I say without game, I mean in a neutral scenario, and with game, which means I have fitness, I have some individuals reproducing more than the others. We observed that the balancing of these phylogenetic trees was smaller, they were more balanced, and when we had games, the speciation process was more accelerated than when we didn't have the game, when it was neutral. So this is one of the signatures left by the incorporation of selection, or the incorporation of cooperation evolution in this case. And something that we are doing now, and it's one of my students is working with, is to understand how extinction, fusion, and speciation reverse, or extinction hybridizations, work in this game, in this situation where we have the selection under a game theoretical approach. So we want to understand if the cooperator species, they are vanishing more frequently, if the hybridization process is mixing species that have different strategies, if the species that are formed, they have different strategies. And we are also exploring very initially the cooperation evolution under different games. We want to understand if different games leave different signatures in the phylogenetic tree. And so far we didn't observe any difference, but this is something we're still studying. And I guess, let me see. That's it. I think I didn't pass the time that I was supposed to do. I'm open to questions if you have. Thank you.